Something, though, I wanted to point out to people. There is a little bit of confusion at times on the strategy box. And I want to remind you of something that was said right at the beginning of the course. I have my required concepts and formula sheet, and it's 2 nice pages. And if you notice, it very nicely tells you basic definitions can be used without justification, but if you use them, you're going to write, I use the definition of in my strategy. Another set of definitions. If you use one of these concepts, you will use, I use the definition of torque, work, power, impulse. They are 2 main concepts for the course. We also have conservation of momentum in there. Notice Newton's laws you can always use. So if you're going to use Newton's second law or Newton's third law, you just write, I use Newton's second law, I use Newton's third law. If you're going to do something like one of these 3 special cases where you're going to use the equations of constant acceleration, you're going to use momentum conservation, energy conservation, these are all ones that you need to tell me why you're using it. And if you're using it for some of these, you better have told me your system. So like energy conservation, you better tell me your system. The same with momentum conservation. I noticed I didn't put that there. I need to put that in. And then there's a final list of a few miscellaneous definitions. If you use any of these ideas, you would tell me you use the definition of one of the following things. So, and of all of these, the gravitational potential energy of 2 bodies and the law of gravity for 2 objects, we didn't really use. It was in maybe one homework. I had you read the section, but you don't have to worry about that. This is it, right? Everything on these 2 sheets is what we did in the class. Everything on these 2 sheets is what you will use to solve the problems on the final. And if you use anything on these 2 sheets, you will tell me in your strategy that you used it. And it's as simple as that. And you can use short little phrases, not big, long, complicated things. Every now and then, look at the solutions. There's one other like conceptual thing you will write. Like, I use the definition of static friction to check if it was a maximum. Right? Because you want to tell me why you set it to equals versus less than to equal or something. So there's a few other limited cases you want to go through the solutions where there's one other thing in the strategy that I would say, but it's almost always something from these 2 sheets. And the stuff that's not on these 2 sheets that gets said is very little, and it's pretty obvious if you see it in the solutions. So as you study, you do want to review the strategy boxes that I wrote and check that. Look at your own strategy boxes from the test you already took. See, did you use this or not? Where did you go wrong? Practice some problems using that. So that's just a suggestion going forward. Any questions on that? Excellent. So now let's turn to, actually jump right into a problem. So we did on Wednesday basically some collisions or explosions where everything was in a line. I wanted to quickly do a case where maybe you have to use components so you can see what that looks like. So we're going to take a ball. Whoops. We're going to take a ball and we're going to throw it at a wall. Now notice, and we're throwing it down at an angle of 30 degrees from the vertical. So this is the incoming ball. So this would be its initial momentum for either problem. Now I wrote the problem a little generically. I say it bounces off at the same speed and angle. What is the average force of the ball? Now there's actually 2 ways we can bounce off with the same angle. I can bounce back up at 30 degrees. So this is case A. Or I can bounce down at 30 degrees. So that's case B. And we're going to look at both of those. So this is P final in that case. And this is P final in that case. And what we're asked about is, in both cases, the force, the average force on the wall. And we notice we're given the time. So we immediately are going to think of what? This is an interactive Friday where you shout out answers. We immediately think of what? Impulse. And we think of impulse because impulse is defined as the change in momentum. but we also know it's caused by an average force times the delta t. And notice everything in our picture is in terms of momentum, and we're asked to find this, and we're given that. So again, except for the angle nature and the fact that we're going at an angle, this is basically that same sort of core nugget single step problem that we've been thinking about and practicing. Questions on the problem? So we'll come back to the clicker question. Whoops. Let's go right to the first version of it, because the first version, I'm not going to ask it as a clicker question, but if you were to pick a coordinate system here, what coordinate system would you work in? Just the direction the ball's going, right? Because everything's in a single line, so there's no reason, we don't need x and y, we don't need components. We can just do this problem, and we can take either out of the wall or into the wall to be positive. I think when I did it in my notes, I took that way to be positive. And so what we see here, if this is P final and this is P initial, we have negative P initial equals P final. And this statement's true independent of which way I pick my coordinate system. But that's the basic situation we have. It's all in one direction. So delta P is pretty easy, right? If I do P final minus P initial, and that's negative P final, I just get 2 P final as my answer. And I was told it leaves with the same speed that it hit with, and we were given the mass. So if I look at all this, the magnitude of delta P is just 2 times 0.1 kilograms times 2 meters per second. So that's mv, and I get 0.4 kilograms meters per second, and my direction is 30 degrees up to the left of the wall. So that's really no different than any of the ones we did on Wednesday, but I wanted to just go through that quickly. Any questions on that? Excellent. So now I want to ask that clicker question. So we're going to do it. Let's just draw it real quickly. We're going to do the other version of it, where it comes in at 30 degrees, and it goes out at 30 degrees. And we're basically going to be asking, do we want a standard coordinate system like that, or do we want what we just did, a tilted coordinate system like that? That's our basic question. So let's vote on that. OK, so most of you are going for an angle. Pretty good. So why are we going for an angle? Why would you pick this coordinate system? Why would that be a good coordinate system to pick? Yeah. OK, so we might get to avoid doing components. OK, so let's start. What I want you to do, write down, right, we're going to be looking for delta P, which means we're going to need perhaps a delta Px, whoops, and a delta Py. And maybe by picking this coordinate system, we don't have to worry too much about components. And we're going to get a force in each of those directions by using that. So quickly write down for yourself, what would delta Px be? What would delta Py be? And again, we'll call this P initial and this P final. And we're going to use that tilted coordinate system because 70% of us picked to use that. And just to make it clear, since that's 30 degrees, we'll tilt it that way, so that's 30 degrees. Okay? I know you probably didn't finish, but you got started. So for the initial momentum, is there any of it in the y direction? Yes, how much? Okay, so this is all a p initial y. What about in the x direction? No. Good, so that's done. Now, for the final momentum, how much is in the y direction? How much? Well, how much is in the x direction? Are you all sure? Or it might be negative. Are you all still sure? Has anyone checked what this angle is? 120. Is anyone disturbed now? If this is 120 degrees, is this lined up with that? No. Right? It's at some angle with that. So we have both py final and p final x. There's both components there. It's not aligned along the x direction. So it's a perfectly fine coordinate system to use, but it doesn't help you as much as you thought at the beginning. Right? I think the 70% of you who picked this had kind of hoped that this would line up with x. Right? But in fact it doesn't, because in this particular problem the angle between the two is not 90 degrees, because I'm having it come off at the 30 and the 30. Does that make sense? So in fact, this problem is a little bit easier to do if I actually pick this coordinate system. Now, I didn't draw this very well because they both have the same speed and they're at the same angle, so they have the same length, right? If they have the same speed, then we know the magnitude of the two are equal, because the magnitude of mv final equals the magnitude of mv initial, because the mass hasn't changed and the speed hasn't changed. Now, given that they're the same magnitude, what do you immediately know from looking at this? There's an isometric thing, and so what's true about p final y and its relation to p initial y? In the y direction, they're opposite? One's going down and one's going up? Look at it closely. In the y direction, they're both going down. Okay, so these two are equal. What's true about p final y related, I'm sorry, I'm saying y again. P final x related to p initial x. Now they're equal but opposite, right? So that is a negative. So now what I have, okay, is the only change in p is the p final x minus the p initial x, and they're equal and opposite. So in a magnitude, it's just 2 times the magnitude of p initial x. And so now I just pick up, in this case, the x component there is 30. This is p initial sine 30. So I pick up that sine 30, and the change in delta p is now 0.2 kilograms meters per second. And so the average force is 20 newtons, and it's in the negative x direction, is one way I can give it, having defined the coordinate system. So comparing the two, you see that it took a greater force. Where's my answer? Yeah. It took a greater force. Oh, I didn't turn that into a force. If I turn that into a force, it's 40 newtons. It takes twice the force to turn the ball exactly around, in this case, than it does to just bounce it down and keep it at the same speed. Yes. There you go. Now, first, any questions on that? Now, what we want to move to, so in this case, notice we had what we call an ideal wall, right? Nothing happened to the wall. I mean, in this case, there's a force of 20 newtons on the ball. What's the force on the wall? 20 newtons in the other direction. Now, the wall didn't do anything. That's because it's, rigidly attached to the floor, and it's a rigid wall, and so there's other forces acting on it. So if you drew its free body diagram, it has no acceleration, and so on, and everything happened to the ball. Now we want to start worrying about collisions where both objects have things happen to them. So the next step, the next part of the chapter, is to really focus on what happens in collisions and explosions. And this is, we're going to focus on both objects now. Right? Up to now, we kind of have been taking the picture. Okay, we have two objects interacting. We know by Newton's laws there's an equal and opposite force. Now we're going to focus on the one object and see what happens to it. So when the cannonball got launched, we focused either on the cannonball or the cannon and asked, okay, what happened to it because of its impulse? When this ball hit the wall, we focused on what happened to the ball because of the force on it from the wall and that impulse. Now we're going to ask, let's take the two objects as a single system. And can we learn useful stuff there? And there's sort of two facts that we take into account when we do this. One is, if I have object A and object B, and they're going to interact. What do we know about their interaction again? Why am I holding up three fingers? Newton's third law tells us what? Equal and opposite. Right? So if I take this thing as a system, right, then we know the internal forces have no net impulse. And we can see that pretty easily because the force on A from B is the negative of the force on B from A. So the change in momentum of A during this interaction is the force on it times delta t. The change in momentum of B during this interaction is the force on B during this time. But this just equals minus the force on A during this time. And so the total change in momentum, when I add the two up, is 0. Notice this is a little bit different than how we might think about forces in relation to the changes in energy. And we're going to come back to this. This is why we're going to talk about elastic versus inelastic collisions. When we had a force between two objects, because we have different forms of energy, we will often focus on one type of energy, say the kinetic energy. So you might have equal and opposite forces between the two objects, but because kinetic energy doesn't worry about the sign, right, the total kinetic energy could change. So a simple case of this is, imagine where I have an explosion. Right? What's the kinetic energy before the explosion? 0. That was an easy question. What's the kinetic energy after the explosion? Large positive number, right? Everybody's flying in different ways. Everybody has v squared. Nothing cancels out. I did not conserve kinetic energy. The forces involved changed whatever the energy associated with the explosion was into kinetic energy. Now, what about the momentum? What's the momentum before? Yeah, again, easy one, velocity 0. What's the momentum afterwards? Has to be 0. The total momentum is still 0. So if you can figure out where all the individual pieces went but one, you'll know where it was. Because now you know the momentum of all of those, you know it has to add to 0, you can find the momentum of the missing piece, and you can know where it went. So in the simple case of an explosion into two pieces, it's pretty easy to know where the other one went if you know where this one went. So that's kind of a difference in collisions and explosions between how momentum behaves and energy behaves, because momentum is a vector and there only is momentum. Energy is a scalar and there's different types of energy. So you think about them slightly differently. The other thing that happens is most of our collisions, we will now, if we're focusing on the two objects, we really will think of them as instantaneous. And we're going to do an example in 2 seconds of a collision where one object is hanging on a pendulum, the other object comes flying in and hits it, and then they stick together, and you ask how it moves. Now, if I draw a free body, if this is my system, just these two objects, I want everybody, we're doing it in the table, so we're near the Earth, draw your free body diagram for my system of the object and the block. Go. You've got a minute to draw your free body diagram. We're practicing our speed testing for next week. How many forces do you have? 2. What are they? You got great weight down because we said we were near the Earth. And what's the other one? Tension up from this rod that's holding it. So, during the collision, do I have a change in momentum? Possibly, right? I might have to worry about which is bigger, the tension or mg. However, the nice thing is the change in momentum is the force times the time. And if we assume our collision is instantaneous, we're assuming delta t is 0. And so the change in momentum is 0. So for most collisions that we will be looking at, we will assume momentum is conserved, assuming it's instantaneous. Now, if the collision takes long enough, then that won't be true. So if, I don't know, I'm a really, really slow Superman, catching a really, really slowly falling Lois Lane, and it takes me a while to catch her, then of course, as we're catching each other, gravity is still acting on us, and we're moving somewhere, and you'd have to worry about that. But at the typical speed Superman is traveling when catching Lois Lane, besides turning her into a mushball when he hits, the collision itself is rather fast. And we can pretty much ignore everything else and just look at the collision as instantaneous and conserve momentum. So 9.9 times out of 10, if there's a collision in the problem, unless I tell you how long the collision takes and ask you for the average force during the collision, in which case you're going to have to use momentum impulse, you will assume the collision takes 0 time and everything happens quickly and momentum's conserved. Any questions on that? Now, of course, once they've collided and you're here, then my free body diagram comes into effect and the objects move. And they obey whatever F equals ma laws are applying to them. Now, the final piece in collisions will be what happens to the kinetic energy. So this is just a quick little test of who read the book. Pretty good. Most of you got it. In this case, it's both A and B. And the key here is this idea of elastic. Elastic means exactly that. We conserve mechanical energy. All of our collisions pretty much at this point, we just said we'll conserve momentum. And they're all going to be at delta t basically 0 and delta x basically 0. They don't take any time or space. So we don't have to worry about there's forces on the objects because those will do work or change momentum after the collision takes place. We'll worry about the collision. Now, that being said, what is mechanical energy? Anyone remember? Since you got the question right, that was good. There's 3 examples of mechanical energy that we have. And since we only have 4 examples of energy formulas, it should be pretty easy to get to 3. What are they? You have a test in a week. Kinetic energy. That's the big one. What else? Spring. And what's the other one? Gravity. So it's basically potential energy plus kinetic energy is your mechanical energy. Now, the other thing that will happen, we will often have problems where there's a collision that takes place on a surface with friction, right? And what is nice, because friction only dissipates if you move a distance d, during that collision, because we assume it happens in one spot, you won't have to worry about friction. So you'll have the collision, and then it starts moving, and now you have to worry about friction. The only time that's not true is if you have a collision where there's a big spring between the two objects, and while they're colliding, they move some distance d that the spring compresses. And now if they're on a surface with friction, I've told you they've moved d, now you have to worry about it. And that gets trickier. Basically, the nice thing is in most collisions which are elastic, they happen without a change in height, so you don't have to worry about MGH. And it's very often just between two objects, there's no spring there. And so at the end of the day, again, most of the time the mechanical energy you're worried about is kinetic energy. That's what you're looking at. If it's not elastic, the reason it's not elastic is it's making a lot of noise, things are deforming, things are sticking together, there's a lot of internal energy, there's some heat, and all this stuff, and we talk about it as energy lost. It's the one time we get a little sloppy, we will say how much energy was lost in the collision. We really mean how much mechanical energy was lost, right? I mean, the energy wasn't lost, it just became other types of energy. Sound, heat, vibrations, mushing of stuff, right? Those are all types of energy. But they're not useful energy, they're not mechanical energy. And so that's why we use that phrase. Any questions on that? Excellent. So now, oh, actually, no, I want to keep doing that. Now, imagine we are now in your favorite crime show. So you're either in CSI, New York, Miami, or LA, or NCIS, wherever you are, and you work in the crime lab, and you want to, now, you actually work in the crime lab, whoa, in slightly olden days where this is a gun, and this is a block of wood. But what you are asked to do, you know, there's been some crime, somebody's been shot, and you want to find the muzzle velocity of the bullet coming out of the gun. It's often an important factor, helps you identify where the bullet may have come from, what was going on, because if you know how fast the bullet's going when it leaves the gun, and you know things about where it got hit, you can use your kinematics, which you're now an expert in. So you need all of this to work in NCIS or CSI. So you can see the practical, we finally get to the real practical stuff. So what you're going to do, and actually this has been done, this is very regularly done for ballistic tests, you have what we call a ballistic pendulum, right? This is a pendulum. It's designed so that when it goes up here, it will stop. Because it has a little ratchet that holds it in place. So it goes up, there's a little bit of friction, but it's not too much. When it gets to its maximum height, it can't fall down anymore. Okay? So the bullet, and there's also a little piece in here to hold the bullet in place. So we will shoot the bullet into our block of wood. It will go to some height. It'll stop. We would measure that height, and then we could determine the speed that the bullet left with. Any questions? So normally you would put on your safety goggles because you're about to fire a bullet into a block of wood, and then you would shoot it in and up it goes. Very exciting, huh? Now, there's a very good chance that if I repeat this, I will break the apparatus. But let me try. Oh, I didn't break the apparatus. That's good. So again, if you missed it the first time, because it goes so fast, pendulum at rest, bullet fired, collision, and it goes up to a height. Now, what I want you to do, the obvious question, if we're going to solve this problem, is to ask ourselves, what type of physics just occurred? So go ahead and ask yourselves that, and then answer it. So as before, 80% of you picked more than one of the above. I'm not even going to bother to show that. Now, we have to ask the obvious question. Our follow-up question is it 2, is it 3, or is it 4 of these? So go ahead and answer that. So pretty large majority for 3. So given that we think it's 3, let's first ask, which is the obvious one that is in here? Well, the big one, we clearly have a collision and catch when the two collide together, right? Now, once again, we're in, well, which one is obviously not in here? And it's not quite as obvious. Ooh, no, circular motion is clearly in here. There's no projectile motion. There's no point. Now, you might say to me, oh, but Professor Dennin, right at the beginning here, it's moving due to gravity. If you notice, we purposely set up our device so that the muzzle of the gun is right next to the block of wood. So it leaves the gun and goes right into the block of wood. So immediately to a collision. Now, if my gun had been over here, then I would have had to worry about what? Projectile motion, because it would have been flying through the air under the influence of gravity, and I'd have to aim correctly so that I hit my block of wood. And when I hit my block of wood, I wouldn't be going perfectly horizontal. I'd be going down at some angle because I would have been falling. So I eliminated projectile motion by setting it up very nicely. So I go straight from a collision to what type of motion is the pendulum doing? Circular. Critical. Because if you identify that as projectile motion, you might use your equations of constant acceleration, which in circular motion do not apply. So we have circular motion, and we have collision catch. Now, once again, we have a type of motion that's not really relevant to the problem. We have the explosion or launch. But we're not, since we're going to ask about what velocity does it leave the gun with, and we're not asking about the impulse that caused that velocity, we're not asking about the force that caused that velocity, we're only asking about what that velocity is. Even though this is there, we don't have to worry about it. So again, depending on how you took the question, it's the same problem we had last time. There are really only two that we have to worry about, but there are three in the problem. So, yeah, sometimes that happens. Now, let's look at these and see how we might build up this problem. And the key is we've identified two motions, a collision followed by circular motion. Now, once you've identified the type of physics, this is why this is such a powerful technique, then the tools you're going to use to solve it get much simplified. Once I have a collision, now let me ask you this. The two things stuck together. Do you think mechanical energy is conserved in this collision? Your answer should be no. Anytime two things stick together, there is, if nothing else, damage being done. Right? For the bullet to stick into the object, for putty to stick to something, something has to happen to cause that stick. There's energy associated with the sticking. Any collision where things stick together are always inelastic. And the only thing you can do is conserve momentum. So right away, for part one, the only thing you've learned in this class that will give you any physics information about that collision is momentum conservation. So that's what you're going to have to use. Now, momentum conservation is part of momentum impulse. So you might be thinking of it that way, but you'll quickly get to delta t being 0 and forces being 0, and so momentum will be conserved. But that's how you want to think. Now, circular motion part. We actually got two routes that we can go. What are the two things we can use for the circular motion part of the problem? Well, we might want to think in terms of the centripetal acceleration, v squared over r, which would tell us that we're using Newton's laws, something with forces. Right? If we're going to use v squared over r, we will use Newton's laws. Now, what's the other option when you have an object where you know exactly where it moves from an initial to a final place? Because remember, here it stops at some final height h. What's the other concept we would use for that type of situation? Energy. Now, which of these two is the one that is best designed for dealing with initial and final, and versus the one that is best designed for dealing with things at a single time? One of those two works best at a single time. One of those two works best for an initial and final. Which works best for a single time. Let's take out your clickers. That's A, that's B. Which works best if you're considering behavior at a single instant in time, like one point in the circle, the bottom of the circle, the top of the circle, the side of the circle? Five more seconds. 3, 2, and 1. Excellent. Almost everybody went for Newton's laws. Newton's laws are things, F equals ma. There's no before or after. There's just that single time. Energy conservation is what we focus on when we're doing the initial and the final. So having taken the time to ask yourselves 2 or 3 simple questions. What motion do I observe in the problem? You pick out the motion. What physics concepts go with that motion? You've picked out the physics concepts. You are now basically done with the problem, right? That is a much, now I admit, I'm way more comfortable with these concepts than you are. But this is your goal. You want to start thinking about these problems in this fashion by asking yourselves these questions. These are the powerful questions that help you get to the solution much faster than any other sort of questions. Because your job on the final with these problems, since they're going to involve multiple physics, is to pick out those physics as quickly as you can. And again, your 2 sheets summarize all the physics we learned. So having our part 1, which I already wrote up there, and our part 2, we can now proceed. Before we proceed, any questions? Did that kind of make sense? We've done this process twice now. We did it Wednesday, and we did it today. Good. So now let's look at it. Part 1, we pick as our system, because we're going to do conserving the bullet and the wood. If I did a free body diagram on that system, we have the tension and the mg down. But that's OK, because we're looking at a collision where delta t is basically 0, so I can conserve momentum. So I'm going to do my before and my after. Now, with conserving momentum, when you make your chart, if you're going to use a chart, there's a couple of different ways to do it. If you look at the sheet I put up on the solution, in this case, I might do it as the bullet, the wood, and the combined, the 2 together. Because those are the objects that show up. What's the momentum of the bullet initially? The bullet initially has 0 momentum? What's the whole point of the problem? To find that speed of the bullet, right? It was fired with some speed. So we'll call that V0. What is the initial momentum of the wood? The wood being our metal cylinder down there. That's 0. What's the combined momentum initially? Well, it's really just those 2 added together. Or you can think of it as not really relevant because it's not combined initially, right? And at the end, those don't really exist. All we have is the combined, which is the mass of the bullet plus the mass of the wood times the velocity of the 2, which I'm going to call V sub I, because it's just starting out to go up. So my conservation of momentum tells me that this is true. So my launch I get just from this. Now notice, there will be some problems you do where you are given that and now you're done. Right? If you have just a simple collision, 2 things collided, like 2 cars are driving along and they hit each other head on and they stick together, and this one was initially going 50 miles an hour and this one was initially going 30 miles an hour, what's their speed when they're done? You would have enough information to solve that problem because you have only one unknown and you have your one equation. So a lot of these collisions, if it's just the collision, you'll be done at this point. Unfortunately, it's not just the collision. So for part 2, right, we now have our system. And here's where we have to be careful. What's our system for part 2? There's 3 objects in our system. Right? We've got our pendulum moving up. What are the 3 objects? the bullet and the wood, because they're stuck together. And what's our third object? The Earth, because we want to use potential energy of gravity. Right? And we know that it's doing circular motion. So therefore the work is 0, and therefore we can conserve energy. We okay with that? So now we make our little table of initial and final. We only have our two energies, kinetic and potential energy of gravity. Our initial is 1/2 the sum of the masses times V initial squared. Our final is 0 because it stopped. We will take h equals 0 to be where the collision occurred. And then the final height is h, so our initial potential energy is 0. Our final is, is the sum of the two times g times h. So as usual, I would equate these two, and my masses will cancel. So I have 1/2 V initial squared equals GH. And that tells me my V initial equals the square root of 2GH. Okay? And now I can take that and plug it in all the way up here to be really messy. And that V naught that I got is M1 is M of the bullet plus M of the wood over the mass of the bullet times the square root of 2GH. And if I wanted to, I could put in some numbers, but that is basically all I need to do. Now the final question you might be asked in the 2 minutes we have while you're packing up is how much energy is lost in the collision. And there you're going to compare 1/2 MB V naught squared with 1/2 MB plus MW V initial squared. And you'll see that this does not equal that, and there's energy lost. And that's the sort of thing we'll talk about on Monday in collisions.